I'm the Chief Performance Architect at Persona. We're a company that specializes in consulting, support, training, and development for MySQL and applications that have MySQL at the center or as a significant part of their infrastructure. So generally, lamp stack consulting, support, training, and services around that. The author of High Performance MySQL and a big admirer of many people in this room. So this whole conference has been about scaling, and I'm almost at this point. I'm wondering if we can find a different word so that I don't have to keep saying scaling, scale. Scalability, all those kinds of things. So I figured we might as well start off with something a little bit entertaining and fun and talk about how you go Webscale. So I see that and I have to say, I'm usually not up with what's popular and hip. And the fact that I have seen or know about this, as I detect from the labs many of you do, is quite a miracle. I just don't really keep up with things like this. Who doesn't know what this is? Anybody? Okay, go to this URL sometime when you have a few minutes to choke up your coffee. It's the full title is MongoDB is Webscale. I left out MongoDB because I don't really want to particularly bash any technology, but it's a very funny. I'll just quote you one line. There's an old developer and an old seasoned veteran, and then there's this new guy who doesn't really know much. And at one point, the new guy says, "Is dev null Webscale?" So let's talk a little bit about Webscale. This comes from a book, which I'm anonymizing, but this is mostly copy and pasted. I hope this is not plagiarism, but I didn't really want to pick on this particular technology. I thought this was an interesting thing for us to think through together and just kind of look at maybe some of the things that people think about sharding and scaling and how you get something really big and how you go hard and fast and long. Right? I said last night, I think in the panel, if I can try and quote myself, I said something like, a lot of problems have seemingly obvious solutions, and smart people think about it and arrive at that solution and try it and find that it doesn't work so well. So this is kind of, in this book, this person was talking about how do you make this database go really big with what seems like a logical kind of approach. But there's some flaws in that. Okay, so the first thing that he's saying is we're going to build this across many, many machines because ultimately we're going to go really Webscale. And you'll see, we're really going Webscale. So we're going to make a proxy architecture where we talk to this database through a proxy, and there's 64 machines behind each proxy. It seems reasonable. Just take that as a granted. I can't really argue with that number one way or another. And there's a terabyte of data on each of those machines. And this particular database needs some maintenance overhead. So it needs about another terabyte of data free so that you can do some maintenance operations. Okay? So including this room for compaction, you need 2 terabytes of disk of data storage apart from the operating system for each of these machines. And so with a single proxy, of course, now you have a maximum of 64 terabytes of real data in these databases that you're actually serving queries against. And for some redundancy, we add in some extra nodes. We go to, this is quoting from the book, you go 2 or 3 times the number of database servers that you really think you need. So each proxy has 192 machines behind it. So let's go with 192 as an upper bound and see what flaws we can find in the system as we go. It goes on a little bit more. So we can multi-layer these proxies. A proxy on top of 64 other proxies, on top of 64 other proxies. So pretty quickly you can see that you get large scales of data right here. So 262 petabytes. That's like on the order of astronomical observatories or super collider observation stations, or there's some other large things that need that amount of data, but not very many. So this is like truly, this is beyond pet scale, right? This is scientific data. If you want large scale, you go to science or you go to Walmart or something like that, right? And as a conservative estimate for the response times for a query against any single layer of this, the author of this book is saying 100 milliseconds, which is probably reasonable. I kind of did a little thinking through. It's a B-tree structured database, and this is a spinning disk, and it's probably a realistic, reasonable number. given that each random lookup from disk might take about 10 milliseconds, and depth of the tree, and a little bit of rotational latency, and all those kinds of things. So with 3 layers, we're up to 300 milliseconds, which is not bad for 262 petabytes of data. And then if we add another, and this is, by the way, another quote from the book, even without performance tuning. Okay? God knows how fast and how far we'd be able to go with performance tuning. And if we add another layer, we can get to exabytes. Is there such a thing as an exabyte data set that anybody knows of? I don't know. I think Google's not there yet. I'm not sure about it. Google is always secret. So what's wrong with this? Anybody? Where does Webscale fall down? Are you going to make me answer this for you? There's a lot that I think is wrong with it. Here's the first thing, is the number of machines that we're actually talking about. So this morning, I clicked on the live chat now at Rackspace. I figured if anybody knows how to rack a lot of machines, Rackspace does. If we take 192, wait, I did my math wrong. I screwed up my math. I'm just realizing this now. Crap. That should be, what should the math be? You know, it should be 64 to the 4th. Because, no, I did my math right, I think. 192 to the 4th power. Right? Wrong? I'm still waffling. I'm not good at math, especially after not much sleep and things on my feet. Anyway, it's a lot of machines, right? A lot of servers for a petabyte. I love the next response. I told him, this is somewhat academic. I just kind of want to know, in general units, how many views do you have in a typical Rackspace data center? Because this is something I'm going to be talking about on a conference. And the agent said very politely, why don't you come back when you have a real problem, and disconnected the chat section. I love this. Regardless of whether I do my math correctly or not, that's a hell of a lot of machines. And you don't just go order up 1 billion, however many, 1,358 million Exchange servers, put them in racks somewhere, stick some proxies in front of them, and then start running queries across them. You don't do that. Right? Data centers don't have that kind of capacity. You don't have that kind of power or cooling. You don't have network bandwidth, all of those sorts of things. There's another serious problem with, let's just take this down to even a smaller size. Let's just ignore the fact that we're talking about sizes that are sort of like physically unachievable here. There was a problem early on, so I'll quote from that on the next slide. For a terabyte of capacity, you need 2 terabytes of disk. Who wants to scale something to petabyte size or even multiple tens of terabytes of size when you need to double your disk capacity? That's really expensive. Okay? So for an exabyte of storage, we need an exabyte of idle disk. And I just did a little back of the envelope calculation, which I may have again done wrong, but it looks to me like 40 megawatts of spinning disk that's just doing nothing other than sucking up power and generating heat. And of course, failing at, I didn't even bother to calculate the mean time between failures. So I don't even know how many people we're going to need, how many of those little like how many of these guys do you think we need running around the data center to plug in new disks as they fail? But that is a lot of idle storage and a lot of power consumed there. I tried to find out how much this was in terms of like nuclear or coal-powered plants. It looks like it's a tenth of the smallest commercial nuclear power plant in the U.S. I couldn't really get Wikipedia to give me authoritative answers on things like how much power comes out of a coal-powered plant. But obviously this is a problem.
That is correct. That number is correct. Okay,
cool. Thank you.
I just calculated the other day just that straight through.
Why am I not surprised that you, just for strange reasons, calculate
nothing to do with scalability.
how much an exabyte of disk will take? Was my other math correct?
I don't think so. I think it was 64 to the 4th times 3.
64 to the 4th times 3. That makes more sense. Yeah, you're right. Okay. right, somebody block me. I'm surprised you all didn't catch me. I want you to call me out, by the way. I'm not very good at these kinds of, just sort of throwing out random numbers. I think in the right general direction, and then I get the details wrong. As every mechanical engineer knows, that's not really a good excuse. So the original proposal that I submitted was why some engineers almost never shard their applications or something to that effect. And the reason why I wanted to go that direction was that for the last, what is it now, at least maybe 6 or 8 years, sharding has been a buzzword. The hype is calming down a little bit these days, but there are still people whose names I won't really name. I'm not going to say that anybody is bad or foolish or wrong or anything, but there's still people who make the circuit tours on conferences talking about how you scale an application. And it typically goes something like this. Let's follow the life cycle of your application. First, you start on a single server. Then you move the web server off to another one, and you got web and a database server separately. And it goes through this, and then you add application, and then you add caching, and then you shard. And this is the inevitable life cycle of an application. And given that you now know this from some big internet authority, you should, whenever you're going to build anything that apparently that has an IP address, you should shard it from the beginning. Because if you don't shard it from the beginning, when you add sharding in later, again, this is all the voice of doom speaking. When you don't shard later, it will be hard. And it'll be so hard that you'll have downtime, and your investors will not love you, and your users will not love you, and things will be very, you'll be a very sad developer, very sad operations. So you should shard early and often, and you should also fail early and often, and all these other kinds of things. And I think that while there's nothing wrong with the life cycle that some of these applications go through, and I've certainly seen many of them. I have worked on many Facebook games that had farm in their name and grew to many tens of millions of users in a couple of weeks. Right? So there's nothing wrong with saying that these things exist. We also need to recognize that they're outliers. And we need to not make anybody feel inadequate if they think sensibly about their application and come independently to the conclusion that they don't necessarily need to follow this same pattern. And especially because shard early and shard often is an incredibly expensive way to do business. And it's actually a pretty good way to get yourself so consumed in other things that you don't make your business successful at all. So sharding back in the really bad old days was when we were all running 5.0.22, and it had some nasty old version of InnoDB in it, and 4 servers, or 4 CPUs, or 4 cores in a server was kind of big, and 8 gigs of RAM was kind of, that was a respectable size for a server. And if you went past that, if you upgraded your 4-core server to 8 cores, you would get retrograde performance improvements. You would actually get a performance drop, pretty significant performance drop. And if you dared go to 16 cores, you really got nailed. Did anybody go to Neil Guther's talk earlier? I know you did. that kind of a performance curve in those days was really common to see in MySQL and InnoDB because it was fundamentally unscalable. And of course, back then we had 15K RPM disks were relatively novel, and of course SSDs were not on the scene at all. And I'm not saying that these two factors, a more scalable MySQL, much more high performance MySQL, and SSDs, I'm not saying that changes the landscape entirely. What I am saying is that with faster hardware and faster software, the combination thereof, we can come a long way. And the thing is that most of the applications that people are building today are not that much larger than they were back then. We just have much better resources to run them on, and particularly on the database server. So we're in, if you're still thinking in the shard early, shard often mentality, you're really some years ago. So I want to talk a little bit about web scaling, because everybody's got their own definition, and I can't argue with any particular definition. I'm just going to use this definition. It's basically the ability to add capacity to a system. Now, in Theo's book, he said, and also remove capacity from a system, which is a good point. But right here, let's just talk about adding capacity to a system while making sure that you add some X to a system while ensuring that something else remains acceptable. And generally, this means adding work to a system, whatever work means. Typically means the ability to handle more, the capacity to handle more requests, while making sure that your response time stays acceptable. On the top, we have this blue line. Sorry for my PowerPoint graphics here, but I'm not very good with anything other than drawing boxes on a screen. So on the top, we have this blue line of tasks all lined up end to end. Man, that system is fully utilized. There's no space between those lines. There are three ways to add capacity to this system. One, you can run more things in parallel. So we've got here apparently a 3 CPU system. You can make the task shorter so that you leave some space in between them, or you can simply do it less often. And a lot of times people will discard those latter two options as ways to add capacity to a system, where they'll say, you know, I need scalability, I don't need performance. Well, if you have good performance, you might not need scalability. And the ability to, I said add the ability for your system to do more of X. On this bottom line, I'm saying stop doing so much X. Am I not sort of like reversing and saying an oxymoron here? Not really, because you may be looking at subtasks here. Let's say that the task that you want your system to do is render the front page of your website, or return an address to a lookup or something like that. The subtasks that you're doing may well be possible to do more quickly or to do less of them. And so that's a perfectly legitimate way to actually add overall capacity to your system. So what I'm getting back to here is that scalability is really about performance. Everything ultimately comes down to raw performance. You don't typically need to think about scalability on its own apart from performance, because it's kind of meaningless without performance. You want me to do a whole lot more of something? Well, why don't I just actually think about how much work I can actually do in a given amount of time with a given amount of resources? And performance is a lot less complicated than people make it. So I spend my life thinking about performance, and I'm not going to claim to be the greatest guru, but even I can get this. Performance should be thought of in two dimensions. One is response time. Absolutely vital to think about response time. You've got tasks that you're asking the system to do, whatever it is. Requests to your database, requests to your application server, requests, dialing the phone is actually a request, right? And you want to know what the response time is for that. You need to measure the response time for that. So that's the time per task. If you flip that on its head, they are not reciprocals of each other, but if you flip it on your head, you get throughput. The reason that throughput and response time are not reciprocals of each other is because of the potential for concurrency. I won't go into this, but just briefly, in case I'm confusing anyone, if you run a whole bunch of 1-second tasks in parallel, it doesn't mean that you get to, doesn't mean that you should divide and assume that the average response time is the reciprocal of the throughput. So the art of optimizing performance. Did you all look at your backpack? We paid the nice folks at OmniTI for the privilege of putting a little white paper in there called Gold Ribbon Performance Optimization. And if you didn't get one of those, Peter Zeitz, my CEO, and I wrote this together with input from Carrie Millsap. And if I had at the time met Neil Gunther, I'm sure I would have credited him as well for influencing my thinking. If you haven't read that, I urge you to read that. It's our humble attempt at trying to help people think clearly about performance and how to optimize performance. But this is really hard. I know I'm putting this very simply on the screen, but let me explain to you how hard it is. The hard part here is in step one. You have to measure, and I've got a little bracket here because Neil taught me something new about measurements today. You have to measure where whatever your task is spends its time. Now, what people tend to do when they look at that is fill in a bunch of invisible words in between, above, below, on the ends. And they start thinking about, you should be measuring counters in the system, you should be measuring what the system is doing, you should be measuring all of these other things. The art of actually optimizing performance consists mostly of getting very tightly scoped and precisely defined measurements of the time consumption of the actual task that you want to optimize, not what else is happening on the system at the same time, but only what you want to optimize. And then once you've got that, that's between 90 and 98% of the work. Once you've got that data, step two, reducing time consumption, should be self-evident. If it's not self-evident, then you've gathered too much data, You've gathered it at wrong scope, for example, you've gathered it system-wide when you should have been gathering it only for a particular task. Or you haven't gathered enough data, or you've measured it wrong, or something else, right? But once you have good measurements, good diagnostic data, the answer is almost always obvious. So away from the digression, here's another thing, and I think Theo said something earlier in the talk this week, that this dichotomy between scaling out and scaling up. Everybody, this is kind of, I guess, about as popular a buzz phrase as sharding has been for the last maybe 5 years or so of my professional life. Scale up, are you going to scale up or are you going to scale up? Scale up, scale up. And the danger of this is that people tend to think there's these two dimensions. I can scale up and I can scale up, or maybe I can scale some combination of this. I can scale diagonally, right? But the danger of this is that it seems to say that's all there is to this. If you thought through this and you thought through that, then you kind of thought through the whole scope of the problem, right? Well, I really do not think that that's a very useful way to constrain the mind. It really boxes things in and eliminates or makes it hard for you to see a lot of opportunities that you might otherwise see. So what I want to talk about here is not scaling patterns or scaling techniques or any of those kinds of things, but to understand what kinds of things does a system actually do, and what are the characteristics of those tasks that make them easy or difficult to scale and get better performance from. So I want to talk about a whole application. I'm not going to talk about any particular application. I'm just going to speak in generic terms. About what makes scaling easy or hard. So again, back to performance. So scaling is about performance. Performance is about tasks and time. And we know that what we need to do to improve performance and thereby either improve scalability or reduce the need to think about scalability, we should think about how to reduce where the time is consumed by that task. And there's basically three ways that a task consumes time. It's utilizing a resource such as the CPU. In other words, it's actually doing production work. It may be doing too much of that production work, or it may be doing it in an efficient way, or not. And that's what, for example, the study of algorithms is about, algorithms and data structures and all those kinds of things. But if it's doing work, then that's one place where you can count the time it's consumed. It can be waiting for a response from something external to the system, such as a disk drive, or a SOAP call, or a DNS lookup, or whatever it is. Or it can be waiting for synchronization. This can be mutexes or any of the various variations on mutexes, such as locks and semaphores and all those kinds of things. Or even at a lower level, at the hardware level, it can be waiting for example, synchronizing a cache line across in an SMP system, waiting for a read to be valid, in other words. And what all these activities have in common, is that they are either easy to scale or not, according to, I would say, these three sort of aspects of each of those activities that the task could be performing. So components that are decoupled from each other are generally easier to scale. I'll give you some concrete examples in a minute, but I think you intuitively know this. I think you also intuitively or even practically know that asynchrony is much easier to scale than things that are synchronous. And components that are stateless are easier to scale. And why is this? It's generally because of dependencies between activities. Whenever you have a dependency between an activity, then you introduce a point at which things have to happen after each other, and therefore cannot happen concurrently with each other. Or there's a dependency, for example, the input of one operation relies on the output of another operation, and so you've got to have that one complete before the next one can start, and so forth and so on. Okay? And all of these three aspects of the system, tightly coupling it or making it stateful or making it synchronous, introduce points that give you less flexibility to move tasks around in time. And the place where I was a little bit fumbling just a second ago, the place where I really want to go with this is that what matters to your users is response time. Okay? And it's response time at the actual user level. So decoupling things, making them asynchronous, or making them stateless allows you opportunities to move the work around in your system or reduce the amount of work that's being done without increasing your response time and therefore keeping your response time acceptable to the users. So again, this comes back to performance and my earlier definition of scalability, which is that you want to increase the amount of work that the system can do while not making response time unacceptable. So app servers are a really good example of something that's decoupled, generally. Your app servers, your Ruby on Rails servers, or Java application servers, or whatever you're running, are generally pretty easy to scale, and you can just throw more of them, bring up more of them in the system, and put them behind your load balancer, or whatever technique you use to distribute load amongst them. And it magically works. And it magically works because there's no dependency between them. Okay? So they delegate their statefulness, usually to the database, or to memcached or to the file system, or something like that. They don't have statefulness that's shared amongst themselves, and they don't maintain that state themselves usually. Sometimes, of course, they're in-memory sessions, things like that. They delegate the inter-process synchronization. Think about your application server before it writes down that somebody ordered something from Etsy, for example. It doesn't go and check with the other application servers first. It just expects the database server to handle that. And this means that you can just throw them all up and scale them easily. And scaling the web server layer of your application is a solved problem, and everybody knows that. It's been a solved problem for a long time. But the reason that it's solved is because it's delegating all of this really hard work and centralizing it, usually on the head of your database server, which means that your database server has to do all sorts of magic and becomes much harder to scale and much more expensive to scale. It's usually your most expensive and difficult and touchy component in your system, right? So here we get to ACID, and I know there are other ways that we can think about database servers, but when I submit my credit card to Amazon.com, I don't want eventually consistent. I really do not want them to lose. You know, they can lose my state, they can lose my shopping cart, they can lose all sorts of other things. But at some point, there has to be a guarantee within the system. And Amazon, financially and legally, has this responsibility, as many of you know, not to charge me something and then not ship it to me. And I used to work in Crutchfield, if you know what that is. It's an audio video retailer, cataloging web marketer. And so I know this very well about, yes, sir?
You made a leap there that I'm not quite following, which is the assertion that eventually the system can lose data.
No, okay, so the comment was that I made a leap to eventually consistent losing data that you didn't follow. Yeah, so that's a fair comment. I'm not connecting the dots there very well. What I should say, to be a little bit more precise, is that when most people talk about eventual consistency, or when many people I've had conversations with talk about eventual consistency, they don't have a very well-defined notion of what it means. And for a lot of them, it means that it's actually okay to lose some data. So here's a good example. People will say to me, and I quote, "Why do I care if I posted a comment to somebody's Facebook page and there was a flaw in the system and that comment didn't get reported? In the big scheme of things, my comment getting lost doesn't really matter." Okay? So what I'm trying to do is draw the distinction between systems that guarantee that comments are not lost in a system and systems that guarantee that my credit card transaction really actually gets committed to disk and is durable and is recoverable and is now in the system. And that my bank account balance is now in the system.
So now we have two problems. So on the one hand, that is not the definition of eventual consistency as it is actually used for systems that are eventual in the system. And two, banks don't work that way either.
I understand that banks don't work that way either, but banks do have a reconciliation process, and banks don't lose my transactions generally.
So again, eventually consistent does not reflect anything about durable. Those are independent concepts.
I'll grant you that and then keep going.
All right.
So back to ACID databases, which is where most of the scalability concerns come in with traditional relational databases. A lot of performance and scalability can be gained by sacrificing some of the ACID properties. But in many systems, you don't want to do that. lot of systems, you don't necessarily have the degrees of freedom that you want to sacrifice ACID properties to gain performance. Which, as I said a minute ago, makes them the hardest and most expensive component to scale. So this was all kind of background, okay? And I'm going to take any system and talk about what kinds of things you do with that system, and think about whether those things are easy or hard. So I'm always going to go back to performance. Forgive me if I sound like a little bit of a broken record on this, but we still have to think about the tasks that you're performing with the system, and tasks and time is what it's all about, especially with database servers, where tasks can be thought of as queries or requests or statements, if you're from Oracle. So there's two fundamental things you want to do with any kind of data. You want to read it and you want to write it. Okay? And each of these has different opportunities for performance optimization all through the stack. And a lot of the things that database servers do for you, or disks do for you, or RAID cards do for you at very low levels are the same kinds of techniques that you can employ at higher levels in your application. And they're very sophisticated and generally very hard to build, but some of them are relatively easy to build and be incorporated into any application. And some of these things will be very familiar. So reads first. Some properties of reads that are interesting for this discussion. First of all, reads are synchronous. And what this means is that I cannot say, for example, would you please look up this piece of information for me? And then go over it and walk away without actually waiting for the answer. Okay. I have to wait for you to get the answer. That's why a read is synchronous. The read is not complete until you've given me the response. And this is actually fundamentally different from writes. Some of these things are different from writes, and some of them are the same as writes. But that's something that you have to think about. Reads can be cached, however. So let's just take this to a low level and look at the operating system cache is probably a good example of a place to do this. It's a reasonable place for reads to be cached. So if it's in the operating system's cache, of course, I don't have to go to disk. I don't have to wait for the arm to move, and the ladder to spin, and the ladder to spin underneath of the arm. And then that data is come back up to the controller and so forth and so on back into the application. So caching, of course, is generally a much faster avenue to get your data. Reads can be combined. This is a little bit funny. I'm going to be talking about write combining as well. Read combining is pretty hard. Postgres does something here, for example, where suppose there's a full table scan that starts, and as it goes through the table, reading those blocks off of disk sequentially, another full table scan comes in. In Postgres, there's an ability for the second table scan to jump in and piggyback on top of the first one, so that the read doesn't have to be physically performed and logically performed again from the operating system's buffer caches. So that kind of combining can happen for reads, although it's very difficult to build in the general case. You might think of it as a specialized case of caching, but I think the mechanisms that you arrive at this performance optimization are pretty different. Reads require 100% of necessary resources. What do I mean by that? I mean that you can't just do part of a read and get the whole result. So I cannot say to you, for example, please look me up that address that I asked you for a minute ago, and expect you to go do some of the work now, give me the result, and then go do the rest of the work later. You've got to do all the work that it requires to give me that answer now. And if you can think of any examples where this kind of falls down, by the way, in exceptions to this, would be interesting to talk about. But I think as a general case, reads being synchronous and reads requiring all of the work to be done are things that we can pretty much count on. And finally, we all know that reads can be done anywhere that the data is, which is essentially another way of saying that reads are cacheable, but it's a little bit, it'll become clearer why I put it in a little bit later. Okay, so writes, we've got a whole different set of properties about writes. First of all, writes can be asynchronous. I can say, please write this down, and then go away and not wait for the response. If I trust you, okay? I can wait for the response, and there are many cases where I want to do that. But generally, I don't have to. So I have a degree of freedom now with writes, which is a good thing. Writes can be buffered. Buffering I'm using a little bit differently from caching. So when I say buffer, I mean store into a temporary location and finish later. So this is one way, for example, that we could do an asynchronous write. It could be buffered until later when it's done. Another way of saying that is that it's delegation to whoever I'm trusting to do the write for me later. Or queued. Of course, the obvious thing that springs to mind there is message queuing systems, such as Apache or Rackspace. And writes can be done with partial resources. I'll give you two examples of this. One is that when I go to my Amazon shopping cart and I check out, it records that the transaction with my bank was completed, but it doesn't actually do, for example, fulfillment. It doesn't allocate inventory. It doesn't print off pick tickets to pull things off the shelves. It doesn't print shipping labels yet. All of that kind of stuff can be done later. So the implications of this write are a whole bunch of other work that doesn't have to happen for the record of this change to become permanent. Okay? Another example where this happens is, I'll speak about the way InnoDB does transaction logging. InnoDB, even within transactions, has something called a mini transaction. And a mini transaction can be a really unbelievably small amount of data, such as a C function, the name of the C function call and the parameters that went to it. And then you can write that down. And you can say, if I crash and I call that function again with the same parameters on the same data, I'm going to get the same results. So if InnoDB crashes and has to recover, we wrote down a very small amount of data that could potentially influence a very large amount of data on the disk. So we did not do all of the work, and we did not record all of the work up front. We recorded essentially the fact that the work has to be done or was done, but we didn't do it. And if you want to keep things consistent, if you want to keep all of your caches in sync, for example, you need to make sure that everywhere you have a copy of the data, when you change it to your master copy, you change all of the copies. Whether that's now or later doesn't really matter, but it does have to happen. So let me just flip back and forth between these a couple of times. So reads are inherently synchronous, writes are asynchronous. Reads are cacheable, writes are bufferable. Reads can be combined, writes can be combined. I actually skipped through that. Okay, so writes can be combined. So use InnoDB as an example again. And I apologize if I'm talking about the technology that you're not familiar with. InnoDB, a database storage engine device. If you update the same piece of data multiple times, you don't necessarily have to write it down to disk each of those times. All you have to do is write it down to disk at some point. And all of those writes that went into memory can be committed to disk with a single write. So that's what I mean by write combined. Reads require 100% of the resources necessary to fulfill the request, but writes can be done with partial resources. And reads can be done anywhere the data is, but writes have to be done everywhere the data is, at least eventually. So this sounds a little bit like the scaling up versus out kind of discussion. How do we get more out of a system in general? We can either get more out of one server, or we can get more out of multiple servers by adding capacity through multiple servers. I like using one server when possible, and it is possible in many more situations than people believe, especially with careful attention to the application architecture and careful, disciplined analysis of the performance and analysis of how to optimize the system's performance. There's a lot of advantages to using a single server. For example, you only have one copy of your data. You never have to think about whether it's consistent, whether you're looking at something that's out of date, whether, perhaps even that there's a data corruption problem where you've got different things in different places saying something contradictory about each other. There's not a whole lot of disadvantages, except that sometimes applications do grow larger than a single server can contain. But I'm going to punt that question and answer that only at the last minute in this talk. The next strategy when you cannot use just one server is to use multiple servers. And I really think that the disadvantages here are, it's pretty much the reverse situation. I think that there's a lot of disadvantages using multiple servers and not as many advantages, although of course when you need the advantages you have. So here's a few ways that you can avoid going past the same server.
We can cover later what those disadvantages are.
No, that's like a whole long discussion that's very application specific.
So there's
I'm not going to talk about it in this talk, though. And actually, I think you can get a pretty good sense of that by listening to the traditional Shard or the Shard often talks. So I don't really think that I would contribute anything by doing that. So to get more capacity out of a single server beyond just performance optimization, which can take you really, really far, you can add more of the resources that you need. And the fundamental resources that anything needs, you can think of them as 4 resources, but really there's kind of 3 classes of resources here. So there's storage, which is disk and memory, there's computing power, and there's the ability to communicate with other processes or other pieces of the application. This is really hard in the cloud, which is one of the ways that the cloud is fundamentally different from what you can do outside of the cloud. In the cloud, and I'm speaking broadly here, but let me just use the cloud as, let's just say that it's the EC2, the Amazon cloud, and use that as kind of a proxy for everything. You don't have control or guarantees over these resources, number 1. And number 2, the resources are lower performance than you can get on physical hardware, dramatically lower performance. So you cannot get anything in the cloud, no matter what storage system it is, no matter what cloud it is, you cannot get anything approaching what you can get from the performance of a directly attached storage system with even traditional 15K SAS disks spinning beyond a RAID controller. You just can't even approach that. And this is economically important among other reasons, because if you really look at the cost, leaving aside the management cost, but if you look at the cost for performance of I/O operations in the cloud, it's very expensive compared to traditional spinning disks. And then, of course, you have solid-state drives, and that changes things in a whole new way. The other thing that you don't have any guarantees about in the cloud is generally the network. The network is shared, and it varies between works okay and is flaky or is unreliable and can be saturated. So you have provisioning problems in the cloud. This is one of the reasons why I wanted to bring this up. Not only do you have provisioning problems, but due to the way the virtual machines work, you can't actually understand your true capacity in the cloud. Because the virtualization technologies, at least the ones in use today, maybe this will change in the future, but they will give you free capacity if no one else is using it, and you don't know whether that's happening or not. So if I'm on a box, I have an EC2 image allocated on a box, and someone else has the EC2 on that same server, the same physical box, and they're not using theirs, and I ask for a whole lot of resources, the Zen virtualization will go ahead and give me all the resources that no one else is using. And I don't know whether that's happening or not. So if someone else's application hits a Mother's Day peak or something like that, I don't know how that's really going to impact me. So it makes capacity planning an interesting game in the cloud. That last, I decided not to read from my last point, and I decided to read from it again. Most non-cloud, outside of the cloud, you can really go far. You can really add a hell of a lot more power to the boxes today. And today, I would consider a commodity server to have reasonably, so at the beginning I said that a respectable machine a few years back was 4 cores and 8 gigs of RAM or 16 gigs of RAM or something like that. So today, I think a respectable server has easily 24 cores and easily 128 gigs of RAM, and can go much, much larger. You've probably heard, for example, the stories from 37 Signals about how they like running on boxes with half a terabyte of RAM. This is not uncommon, and these are still commodity. You may think it's not commodity because it's not for the average guy, but the definition of commodity is actually interchangeable parts that are readily available and don't really differ much between vendors. So these boxes are commodity, even though they may not be affordable to everybody. So that's a whole different ballgame than we were talking about a few years ago. You can really go far by adding more horsepower to just raw performance at the hardware level of your server. And by the way, MySQL these days takes much better advantage of that too. So single server method number 2 is to avoid using the slow resources. And this is just in general. I mean, I hope that when you are optimizing the performance of something, you'll actually measure what resources it's using and which of those are consuming time. But in general, if I were to say best practice or something fluffy like that, I would say avoid using the slow resources. So avoid using the disk, because the disk is slow and it's very far from the CPU where actual work gets done. And even SSDs are very, very far from the disk where actual work gets done. So you want to avoid using those. And What that generally means is that a database works well when the working set fits entirely in memory. The working set is a fuzzy concept. It means the data that the database really needs to do most of its work. Not necessarily all of it. You probably want to think about some distribution of data. I don't know whether you want to think about it as a percentile or what. I haven't found a really good way to quantify and measure what a database's actual working set is yet. That works in all situations. In some cases, I can say this is your database's working set because, for example, I ran your workload in a simulated test against it, and I can see that it only touched 4 gigabytes of your 32 gigabyte total data set. So your working set is at least smaller than 4 gigabytes, but it may be much smaller than that, right? It might be, even though it touched 4 gigabytes of data there, maybe only 512 megabytes of that was really in your hot working set. But databases work well when the working set fits entirely in memory and it doesn't have to go out to these slower resources. So this is a great way to improve the performance of your database server and get a lot more out of a single machine. And there's a whole bunch of ways that you can ensure that your working set fits in memory. One of those is to reduce the size of the working set. And this is one of my first 3 courses. The last couple of jobs that I worked at before I joined this consulting company, I was privileged to work with a man who had a long time ago learned the purging and archiving religion. And I began to understand his wisdom as we worked on scaling a very large advertising database. And I've seen it many times since then, that for example, when I go into a customer and I see that they're storing the log data in the database, that's a clue that somebody's not really thinking about the physical layout of that data and what that's really costing them. Old orders. Does your website really need to have old orders in the same tables that the website itself is reading from? Or can that actually be the old invoices and old order information actually be moved off to another server? Let's say after the order is fulfilled, give it 30 days because that's the return period. Move it off to another server. Get it out of your server completely. How often does somebody look at their past orders? I know I've looked at my past orders using Amazon.com probably 3 or 4 times, and I've ordered a lot of stuff from them. And for the times that I actually looked at those old orders, it would have been well worth it. If I'm a typical user, it would have been well worth it for them to have that on another server and build some application logic in to redirect for old history to another set of servers and keep their operational servers extremely small. Another example of this, well, I'll just do that one. Just that one example. Another benefit of purging and archiving is that you actually keep your hot data closer together and therefore reduce the working set size even further. So locality of reference. Summarizing. If you want to count how many of their products there are in a category or something like that, you don't have to scan the products table every time. You can maintain redundant copies of this data and read that from the summaries, because you probably don't update your product catalog that often, right? So you can easily amortize those reads across the number of extra writes that it's going to take to maintain the summary table. Compression is a big deal for certain types of data. Sometimes the data are very compressible. Others you don't necessarily want to compress because of the properties that compression might have, but it's an option you should be thinking about. Using the smallest data type, so don't store IP addresses as strings, so in this intrusion, that's kind of the flock to death example over there. And schema design and physical layout, including the clustered indexes if your database supports them, can be very common. And when one server isn't enough, there's a couple of other options that you have. So you're going to have to exceed your resources on your one server are going to have to be exceeded by something. You should be thinking about what that is, whether it's reads or writes. And there's 2 primary options here. You can duplicate or you can partition your data. So for duplication, caching is a way of duplicating data, right? So memcache D. Replication is actually another way of duplicating data. Indexes. Indexes always have at least some level of duplication of the data that they actually refer to. CDNs is just another way of caching. These are all just examples. Materialized views, even the summary tables that I talked about a little bit earlier. So duplicating data is useful for increasing read capacity because reads can be done anywhere. However, it is not useful for increasing write capacity because the writes have to be done in all of those copies if you want to keep them up to date with the canonical copy. So hard problems with caches. There are two hard problems in computer science: naming variables correctly and expiring caches, right? I don't remember who said that. Was that you? Anybody know? I forgot. Anyway, it's a little bit tongue-in-cheek, but it's true that expiring caches is a hard problem, because if you don't do cache management correctly, then your users will have an inconsistent experience. I post a comment on the page, reload the page, and my comment isn't there. Why? Because I posted the comment to the master database, and my page reload came from the slave database that's delayed in replication, and it took a little bit of time, and I hit the slave before the replication delay. So the drawback here, I would say the major drawback here, in MySQL, I'll come to that one a little bit later, but the major drawback here that I see is a little bit surprising. People don't really think about it. Aside from the application level things, that one of the major performance and resource consumption drawbacks here is that each copy consumes those resources over and over again. So why would I want to have multiple copies of my working set in memory on a whole bunch of different servers and just be running essentially duplicated, redundant hardware and operational efforts and all those kinds of things to keep that up to date. If you can get away from it, it's nice not to have to. And you can do some tricks. For example, one that I'll mention here to increase locality of data is that you can do even simple schemes sometimes can help to make sure that similar requests always go to one of your replicas and similar requests always go to another of your replicas, so that their hot data set that fits in memory and is the least recently used tends to remain similar, so you're not completely duplicating and losing the benefits of locality reference. And I'm really getting to the end here, and I'm finally mentioning the need for sharding. And there's essentially one thing that might force you to do sharding, and that is when you can't serve the write capacity on a single machine. That's when you have to partition things up and spread it across multiple machines. So I won't bore you with all the details. One thing I'll mention is that sometimes with MySQL, you're still forced to shard before you really need to, because replication is single-threaded, and every system has its limitations. So there are going to be limitations that are going to limit the scalability of your system in all sorts of different databases in all sorts of different ways. But I'll just mention here that in a multi-threaded workload on the master, if you're executing that again on the slave as a single thread, there's no way that the slave can keep up with a reasonably powerful master, even if the slave is much more powerful. So there's lots and lots of different techniques that I've used successfully in the past to avoid what seems like an inevitable need for sharding, and sometimes to grow systems much, much larger than people thought that they could be grown, including resorting to writing things in shell scripts and using the file system and writing small purpose-built C applications to do things like pre-aggregation before you load it into that precious, expensive, hard-to-scale database. And there are lots of things that I think I don't have really time to talk about that. More options. Here's one of the interesting ones here, the delayful updates. So this, you can think of this as write down that the order was received, but don't do all the work that's necessary to process that. For example, just log the change instead of performing all of the work that change eventually implies. And here's a couple of books from people who are at this conference that I encourage you to check out. This is from John Oswald, who's spoken a couple of times. There's a very clear explanation of capacity planning. This is Theo's book, Scalable Linear Net Architectures, very good read. This is Neil Gunter's book, a good read for the more mathematically minded of us, capacity planning. And this is my book about MySQL performance. And you can reach me here, and if you have any questions, we have about 4 minutes. Yes?
Not so much a question as a comment as far as caching, and especially with buffer cache in MySQL is concerned, we're running very large ones. At 37 one of the issues that we had was if we ever got into a situation where we had to go from master to a slave, and the slave had a cold cache, the site could be essentially unavailable for hour-long if we didn't know in advance.
Yeah. Okay, so the comment was sometimes when you fail over, the machine that you're failing over to isn't truly warm, especially if it's a replication server that is only that's idle and is only running the right workload that it inherits from the master, the state of the caches on that machine can become dramatically skewed from the state of the caches on the machine that serves production traffic, and it can take literally hours for the server to properly warm up and be serving responses in an acceptable response time. And I think, do you mind if I mention one? Okay, so we wrote a plugin for one of the Modification tools to help solve this problem with 37 signals, where we mirror production traffic, the read-only production traffic, from the active production master onto the standby slave. And one of the reasons why you might want to do that instead of actually serving reads off the slave is so that you don't mask a lack of capacity on your slave, lose one of your servers, suddenly you find that you're relying entirely on your failover machine and no crack. Since the last time this happened, our capacity, our demand is actually more than our failover machine can handle by itself. Right? So there's a bunch of reasons why you might want to run a completely idle standby machine, but not actually keep it completely idle. You want to keep it serving something that resembles a production workload. So that when you do a failover to it, it's fast. Yeah?
Is there anything you recommend for it? I've been on one server, but I want to have a web system that's geographically distributed. Like so I'm in Ford, data centers around the world. I've been on one server, but I want to keep the data close to the web server. So I don't have to end up, one master, multiple slaves, local to the particular data centers.
Okay, so the question is, if you're geographically distributed, how can you keep the database close to each of these application servers? Yeah, and it's small enough to fit on one server, so you don't need to do anything fancy. You just need to make sure that you're not reaching across the network a long distance to get your data from your database. Yeah, I would just use regular replication for that if you're writing column location. If you're using MySQL or whatever you do, don't do ring replication with multiple